guys, this video is for the Module 6 review for the Semester 1 final. I'm going to do 3 examples here dealing with polynomials. Some things I put in the notes were just about end behavior. LC here is leading coefficient. So if it's a positive leading coefficient, even degree polynomial, those are the ends, and there's the rest of them there too. So we are in this unit, we did a lot with finding zeros of polynomials, and one of the things we used to do that was division. So we learned how to use long division with polynomials as well as synthetic, so I'm going to do an example with each. So this first one I'm going to do long division. Why I'm choosing that is because I have a leading coefficient on x that's not 1. So I have 3x to the 4th plus 12x to the 3rd plus 6x plus 24, and I am dividing that by 3x plus 12. So remember to do this, we are looking at those leading terms, and I'm asking, what do I have to multiply 3x by to equal 3x to the 4th? I'd have to multiply by x to the 3rd. So now I take x to the 3rd and I multiply by this term, so 3x times x to the 3rd is 3x to the 4th. My goal is to get these to match, and then x to the 3rd times 12 is 12x to the 3rd. So right now these are both positive. Draw the line, change the sign. Those should go away, and actually I get the next 2 terms to go away as well, and I bring down the 6x and the 24. And now I repeat. So I'm looking at 3x and 6x. What do I have to multiply 3x by to equal 6x? I have to multiply by a positive 2. So 2 times this thing is 6x and 24. And draw the line, change the sign, and we actually get everything to go away, so I have a remainder of 0. So depending on kind of how you're asked to write your solution, this divided by this equals x to the 3rd plus 2. That's what we got when we did the division. Sometimes they might have you write 3x to the 4th plus 12x to the 3rd plus 6x plus 24, we might say that that's equal to our divisor. So 3x plus 12 times the quotient, which is what we got for the answer, and then plus the remainder. Ours is 0, but if it wasn't 0, we would put whatever it is out here. So this is another way you can write your solution. So it kind of just depends on how you're asked to write it. Okay, number 2 says find all the roots. Okay, so for these problems, what we did is we graphed. So use your graphing calculator. You're going to enter this function into y equals. Okay, I've already done that. And then you're going to hit graph. You might need to adjust your window. So I can see it looks like it's crossing right at 3, but remember you can check that. If you go to your table, so second graph, and I'm looking for when y is 0. So y is 0, x is 3. So that is actually a 0 of this function. Or remember, you can go to second calc and go to 0. And it'll ask you left bound, right bound. So you move that little blinking guy just a little to the left of your 0, and then a little to the right of your 0, and then guess. And so it does give me the 0 of 3. So a couple ways to do that. So we know 3 is a 0. But this is a 3rd degree polynomial, so I should have 3 zeros. So I only see one place where it crosses the x-axis, so it's likely my other 2 zeros are complex, okay? So we are going to find that by dividing out this 0. And I'm going to use synthetic division this time. So whatever we're dividing out, that 0 goes in the little box. We list all the coefficients here, so I have 1, -2, -2, -3. Okay, we're going to bring down the first one, and we're going to multiply. 3 times 1 is 3, and then we add. -2 plus 3 is 1. 3 times 1 is 3. -2 plus 3 is 1. 3 times 1 is 3, and then add the last one. This last number is your remainder. So again, we got a remainder of 0, which we should if this is actually a 0. So now what's left is 1 degree less than this, because we divided out 1 0, and so there's 2 remaining. So this is a quadratic function now. So it is 1x squared plus 1x plus 1. Okay, so now I'm going to complete the square, use the quadratic formula, or something to find the other two zeros. I'm going to go ahead and use the quadratic formula. Okay, so we have x equals negative b plus or minus square root of b squared minus 4 times a times c. All of my a, b's, and c's are 1 here. Okay, so let's simplify. So we've got 1 minus 4, which is negative 3. Okay, so let's just write it in terms of I. So we got negative 1 plus or minus I root 3 over 2. Okay, I can't do any simplifying there, so those are my other two zeros. So I'm just going to add it to my list up here, negative 1 plus or minus I root 3 all over 2. So those are my zeros. I have 3 of them, which should match the degree of my polynomial. Okay, this one has asked me to write the equation for a polynomial function that has a degree of 3, and they're giving me a specific point. When x is 0, the output is 4. And we're given these zeros. Remember, anytime you have a complex zero, its conjugate is the other zero that makes it up. So my zeros are actually 1, 4i, and negative 4i. So if I were to write this in factored form, we have p of x equals, we have some leading coefficient possibly, and I don't know what that is, so I'm just going to call it a. And then I'm going to write my expression in factored form. So I've got x minus 1 if 1 is a 0, x minus 4i, and x plus 4i. Okay, so we can leave it in factored form, but we don't want to write it with i's. So we're going to go ahead and I'm just going to multiply this together. So x times x times 4i, and negative 4i times x, negative 4i times 4i. You might recognize this as difference of squares. So what it turns into is x squared minus 4i squared, which is x squared minus 16i squared, which is x squared plus 16. So we have x minus 1 and a. Okay, so now they actually want me to find what is the value for a, and that's why they give me this point. So I'm going to put in 4 for p of x and 0 for all the x's. Sorry, 0, not 1. Okay, so if we simplify here, I have negative 1 and 16. So we have 4 equals negative 16a, so a is negative 1/4 when I do that division and reduce. So my final polynomial equation should be negative 1/4 times, then I'm going to leave the rest in factored form, x minus 1 and x squared plus 16. And I'm going to leave it like that. You could distribute, but it's not necessary. This is actually preferred. But that leading coefficient is important because now that tells me something about the end behavior. So solving for that a is necessary. If they give us a point, we can do it. Okay, that's it for the Mod 6 review.